Good morning everyone. So, we were looking into the similarity solution for the similarity solution method for the solution of partial differential equation. In the last class, we chalked out, we elaborated about the when a similarity solution method can be utilized for chemical engineering problems. The typically the whenever you will be having a self similar profile in the definition of the problem, then we may be having a similarity solution method. By doing the similarity by self similar profiles means we are talking about something like boundary layer profile. If you remember that the boundary layer profiles are like velocity boundary layer or mass transfer boundary layer or thermal boundary layer, the concentration profile and temperature profile in case of thermal boundary layer, they will be self similar in nature. So, one can have a similarity solution method in those cases. Now, what is the advantage of similarity solution method? In the similarity solution method, one can reduce the number of variables from 2 to 1. So, therefore, if you have an original problem which is having two independent variables, that will be basically giving the governing equation of partial differential equation. By similarity solution method, we will be defining a combined variable which will be a combined variable of the two independent variables. So, and the dependent variable can be expressed as a function of this parameter only. So, this is known as the similarity parameter or combined variable parameter. So, therefore, the governing equation now has become ordinary differential equation. So, from partial differential equation, it will be reduced to ordinary differential equation, and the solution of ordinary differential equations are always simpler and easier compared to the partial differential equation. We also looked into two thumb rules where the similarity solution will be applicable. First thumb rule is that the partial differential equation must be a parabolic partial differential equation, and secondly, one of the boundary condition must be residing at infinity. If these two conditions are satisfied, then one must be may be having a similarity solution or may not be having a similarity solution. But so these are the sufficient conditions. That means, if the similarity solution is there, these two thumb rules have to be satisfied. Next, we took up a problem. We could not finish the problem in the last class. The problem was Stokes' first problem. Let us define it once again. What is Stokes' first problem? In case of Stokes' first problem, we have a pool of liquid there in the and it was stationary in nature initially. Now, we place a plate at time t is equal to 0 in the stationary pool of liquids, and at t equal to 0 plus we starts it this plate starts moving in the forward direction with a velocity u naught. So, we fix up your coordinate system here y, this will be in the direction of x. So, at t is equal to 0, the plate starts moving in the forward x direction with a velocity, a constant velocity, uniform velocity u naught. So, what happens at time t is equal to the fluid particles close to the plate, they will be having the similar type of velocity u naught in the forward x direction because of no slip boundary condition. As you go away from the plate in the y direction, the fluid, because of the viscous forces, the velocity of the fluid particle in the x direction they start decreasing. So, what will happen after that? After that, when beyond a particular point, the fluid particle will be having the velocity will be decreasing, and it will be decreasing to the 0. So, the beyond that particular point, the fluid particle does not experience the presence of this moving plate located at the origin. So, let us write down the several assumptions that we require to solve this problem. So, these assumptions, let me list down this assumption. Fluid is incompressible. That means the density is constant. Second assumption is it is a one dimensional flow. That means y component velocity is not equal to it is not present there, and third assumption is that z dimension is too long. That means the variation del del z, any derivative with respect to z is equal to 0, as well as the velocity component v z is equal to 0. This v y is equal to 0 one dimensional flow. For z dimension too long, we have v z is equal to 0. Now, once we have this, let us write down the equation of continuity and equation of motion in the x direction. So, if you do that, the equation of continuity will be giving you the following expression. We write down equation of continuity in its full form: del rho del t plus rho del v x del x plus del v y del y plus del v z del z is equal to 0. Now, this term will be gone because the fluid is incompressible. Okay. And del v y del y, v y is not present there. So, v y is equal to 0, and this last term will be equal to 0 because del del z of anything is 0 or v z is equal to 0. So, what we will get from equation of continuity is that del v x del x is equal to 0. That is a very important relationship which may be utilized for the simplification of equation of continuity, equation of motion. Let us write down the equation of motion in x direction. Let us write down the full form of equation of motion: rho del v x del t plus v x del v x del x plus v y del v x del y plus v z del v x del z is equal to minus del p del x plus mu del square v x del x square plus del square v x del y square plus del square v x del z square plus rho g x. G x is the x component of the body force, the gravity force. So, let us look into the various terms of the Navier-Stokes equation in the x direction and see what these terms they represent. The first term on the left hand side, it represents the transient term or local derivative term. The rest three terms on the left hand side, they replace the convective term or the inertial term, the inertia of motion, and on the right hand side, the first term is the pressure gradient term, the second term, this mu times all these three terms, they are basically the viscous terms, and plus rho g x is the body force, where g x is the x component of the gravity. So, now let us simplify this equation. This term will be remaining as it is, then del v x del x is equal to 0. This is because of equation of continuity. V y is equal to 0 because of our assumption that in the y direction the velocity component is negligible. V z is equal to 0 or del del z equal to 0 because z component does not exist. Third, the first term on the right hand side, del p del x is equal to 0 because there is no pressure gradient in this system. The motion is because of the quiet flow, because the movement of the wall, there is no pressure gradient present. So, therefore, del p del x is equal to 0. Now, del v x del x is equal to 0. You differentiate this equation with respect to x once again. So, this becomes del square v x del x square is equal to 0. So, first term will be off, then del square v x del y square, this term will be there, and del del z square is equal to 0. because del del z of anything is equal to 0, and there is the x component of g will be equal to 0, because g is only in the minus y direction. So, we do not have any x component of g. So, therefore, what we have is rho del v x del t is equal to mu del square v x del y square. Okay. So, now del v x del t is mu by rho, that is nu del square v x del y square. So, this becomes the governing equation. Nu is nothing but mu by rho. This is known as kinematic viscosity. So, this becomes the governing equation. Now, if you remember, if you see this equation, V x is a function of time and y. So, that can be interpreted from equation of continuity as well. If you look into the equation of continuity, del V x del x is equal to 0, this simply means V x is equal to a function of y and t. Okay. Now, let us write down the set up the initial condition and boundary condition for this problem. The initial condition is that at time t is equal to 0, V x is equal to 0, at y is equal to 0, we have V x is equal to u naught, that is the uniform velocity. At y is equal to infinity, V x is equal to 0. Now, let us discuss this boundary condition. So, this is the plate, this is y direction. So, the velocity becomes 0 when you go away some point in your system in the y direction, but what is that point? But definitely, so it may be some point here, it may be some point there, it may be some point there, but you do not know a priori at what point, at what y location V x is equal to 0. So, therefore, the convenient boundary condition for this problem is at infinite distance in the y direction from the plate, velocity will be equal to 0. So, we put this boundary condition at y is equal to infinity, V x is equal to 0. Now, let us non-dimensionalize this problem. We write V x star is equal to V x divided by u naught. We write y star is equal to y by L if the length of this plate is L, and we will be automatically getting the the non-dimensional time. So, if you put all this in the del V x, so this becomes del V x star del t in the governing equation, nu L square del square V x star del y star square. So, this becomes L square by nu del V x star del t is equal to del square V x star del y star square. So, this becomes del V x star del tau is equal to del square V x star del y star square. So, tau is non-dimensional time is nu t over L square. Now, let us set up the non-dimensional boundary condition. At tau is equal to 0, V x star is equal to 0, at y star is equal to 0, V x star is equal to 1, at y star is equal to infinity, V x star is equal to 0. So, these are the boundary condition of this problem. So, if you look into the governing equation and the boundary conditions, this equation is purely a parabolic partial differential equation, and one of the boundary condition is residing at infinity. That means, this problem satisfies the thumb rules of a problem to be which will be admitting a similarity solution. So, therefore, we can have a similarity solution for this particular problem, but before going for the solution one has to get what will be the similarity parameter or the combined variable parameter, so that we can make this equation to be expressed in that parameter only. So, next exercise is getting the similarity parameter. So, for obtaining the similarity parameter, what we do, we evaluate the governing equation we do an order of magnitude analysis. Del V x is, let us say, the change in is delta V x star, and del tau, let us say from time t is equal to 0, the change is tau minus 0, that will be roughly equal to del square V x. Del square V x, if you remember that, if you remember the numerical stuff, the del square V x is nothing but some kind of delta V x. It is second difference. That means, if you have a discrete variable, let us say y and V x, then let us say you have the terms like here. So, delta V x will be given by this minus this. So, you will be getting this difference, this minus this. So, you will be getting a difference in between, and delta square V x is the difference between the two. So, it is being there, then you will be getting a difference between the two. So, it is also some kind of delta V x star, and delta y star square is at the edge of the boundary layer. So, it will be delta star square minus 0 square. Okay. So, we do an order of magnitude analysis at the edge of boundary layer. So, what will be getting that 1 over tau is equal to 1 over delta star square, and delta star is nothing but root over tau. Okay. So, if you remember, in the last class we have talked about, if we write down the similarity parameter in terms of delta star divided by independent variable, then all the curves will collapse on single curve. So, we define a similarity parameter in this case. Parameter eta, and that eta becomes y by delta star. So, therefore, you will be having y star by delta star. So, this eta becomes y star divided by root over tau. Okay. So, this becomes a similarity parameter, and we can have the similarity, we can express now the similarity parameter, the various differentials of the governing equation in terms of similarity parameter. In fact, this is one of the method how the similarity parameter is defined in case of boundary layer analysis. So, we expressed the partial derivative of the governing equation in terms of eta, so that the partial differentials becomes total derivatives. So, del V x star del tau will becomes del V x star del eta and del eta del tau by the chain rule, and this becomes, since V x star is now a function of eta only. So, this becomes a total derivative d V x star d eta, and del eta del tau will be nothing but minus half y star tau root tau. It becomes basically tau to the power 3 by 2. So, it will be minus 1 by 2. This y star and tau, y star divided by root over tau is nothing but eta. So, this becomes half eta by tau d V x star d eta. Similarly, we will be getting del V x star del eta is nothing but d v x star d eta and d eta dy by the chain rule. So, this becomes 1 over root over tau d v x star d eta, and then we took so this is del v x star del y star. We do the second derivative, one more derivative of that, del square v x star del y star square. So, this is nothing but del y star del v x star del y star. So, del eta del v x star del y star, we write this expression 1 over root over tau d v x star d eta del eta del y star. Del eta del y star is again 1 by root over tau. So, this becomes 1 over tau d square v x star d eta square. So, we get the different derivatives of the governing equation in terms of the combined parameter or the similarity parameter eta. So, let us see what is the form of our governing equation. If we write down in the form governing equation, this becomes 1 by tau d square v x star d eta square is equal to minus eta by 2 tau d v x star d eta. Tau will be cancelling out. So, you will be getting d square v x star d eta square is equal to minus eta by 2 d v x star d eta. Now, this is the form of the governing equation in terms of the similarity parameter eta, and you check please that partial differential equation has now boiled down to ordinary differential equation. Let us set up the non-dimensional boundary condition in terms of eta. At y star is equal to 0, that means at eta is equal to 0, your v x was equal to u naught. So, it will be v x star is equal to 1, and at eta equal to infinity, your v x star is equal to 0. Now, this problem can easily be solved now. So, we have to define, let us say d v x star d eta is equal to z. Okay. If you define this thing, then you will be getting d v z d eta is equal to minus eta by 2 z. So, bring it to the other side. So, d v z this becomes d z, right. D v x star d eta equal to d z, that means d v x star d eta square will be nothing but d z d eta. Okay. We will write it down. So, we define del d v x star z d eta is equal to z and express this equation in terms of z. So, if we do that, what we will be getting is, we will be getting d z d eta is nothing but minus eta by 2 z. So, d z by z is nothing but minus eta by 2 d eta. Integrate this out. So, this becomes ln z is equal to minus eta square by 2. So, it will be eta square by 4 plus some constant, let us say that constant is ln k 1. So, z becomes k 1 exponential minus eta square by 4, and z itself is d v x star d eta is equal to k 1 exponential minus eta square by 4. So, v x star becomes k 1 integral exponential minus eta square by 4 plus another constant k 2. So, this gives the profile of velocity within the boundary layer, and there will be d eta there. So, it will be, so you have two constants of integration k 1 and k 2. These two constants have to be evaluated, but that by the two boundary conditions. If we put the boundary condition at eta is equal to 0, v x star is equal to 1. So, that means 1 is equal to k 1, and this integral from 0 to eta. So, it will be effectively 0 to 0 exponential minus eta square by 4 d eta plus k 2. So, when you evaluate this integral from the same limit, the whole integrum becomes 0. So, you will be getting k 2 is equal to 1. So, once you get k 2 is equal to 1, let us look that what is the form of profile. So, this becomes 1 plus k 1 0 to eta exponential minus eta square by 4 d eta. Now, we have evaluated one constant, we have to evaluate the other constant k 1. Let us put the other condition that is at eta is equal to infinity, v x star is equal to 0. So, therefore, 0 is equal to 1 plus k 1 0 to infinity exponential minus eta square by 4 d eta. Now, if you look into this integral is a definite integral because the values from 0 to infinity. So, how to evaluate this integral? You can evaluate this integral by doing a numerical integration by maybe using a trapezoidal method. Okay. So, the infinity you can take some high value, maybe 5 or 6. So, if you put the upper limit as 5, evaluate this integral, then if you then change the upper limit from 5 to 10, if the integral does not change in the significant places, maybe 3 or 4 decimal place, then you can say 5 is the infinity for this particular problem. So, we call this definite integral as I. So, k 1 is nothing but minus 1 over minus 1 over I. So, v x star, the profile of v x star as a function of eta will be nothing but 1 minus 0 to infinity exponential minus eta square by 4 d eta and 0 to eta exponential minus eta square by 4 d eta. So, this is the form of the velocity profile in terms of the combined variable. Now, if this will be from 0 to eta. So, if anyone wants to plot in terms of x and y star and tau, can free to do, because eta is known as y star divided by root over tau. For a fixed value of y star, one can plot eta one can plot v x star as a function of time. If you would like to plot what is the velocity profile at y star is equal to 0.1, put the value of y star as 0.1, then put a do loop where the tau will be changed from 0 to some in a loop, and then you will be computing this equation on the right hand side, and you will be getting a profile of v x star as a function of tau. Similarly, if you want to put what is the profile of v x star at different points of tau with as a function of y star, then what we do? So, for a fixed value of tau, let us say 0.5, we put the value of 0.5 and eta becomes y star by root over 0.5, and evaluate this integral under a loop of y star, so that you can get a profile of v x star as a function of y star. So, that is how the similarity parameter can reduce the partial differential equation into an ordinary differential equation, and you will be almost getting an analytical solution in this case. Okay. Next, we will take up one more example of similarity solution, that is in membrane separation application. Suppose you have a membrane here which is porous in nature, and the flow is occurring into a thin channel of, let us say, the height the full height is 2 h, the half height is h. So, we fix our coordinate system y here, x there. We assume a steady state process. So, in this case, the solid particles, the whole operation is under high pressure. Though because of the pressure, the solid particles will be depositing over the membrane surface, forming a thin concentration boundary layer. So, this is a thin mass transfer concentration boundary layer. We assume that the in fact, the permeate flux, the permeation velocity will be maximum here, because the thickness of this boundary layer will be governing the resistance against the solvent flux. So, lower the thickness, then the higher will be the permeate flux, then this flux will reduce and then it becomes almost constant. So, the permeate flux V w is a function of x. Next, we assume that the axial velocity is order of magnitude higher compared to the permeation velocity. So, therefore, we assume that the laminar velocity profile remains undistorted because of the suction at the wall. So, therefore, we can say that this profile remains still laminar. And what we do next is that we would like to find out what is the concentration profile in this mass transfer boundary layer or concentration boundary layer. So, our aim is to obtain concentration profile within mass transfer boundary layer. So, in order to do that, let us write down the velocity, the concentration field within the boundary layer 0 to let us say delta. So, let us write down the solute balance equation within mass transfer boundary layer. If you write down the solute balance equation, this is also known as the advective equation. So, it becomes u del c del x, and we write down the and we assume the system is operating under the steady state. So, u del c del x plus v del c del y is equal to d del square c del y square. So, this is the advective equation we would like to solve within the mass transfer boundary layer. Now, once we will be able to solve this equation once we get the velocity field u and v appropriately within the mass transfer boundary layer. So, if you look into this, we write down the velocity field and we have assumed that the flow is laminar and the parabolic velocity profile remains undistorted. So, 3 by 2 u naught into 1 minus y minus h over h square. This is the parabolic velocity profile within the in a rectangular thin channel. Parabolic profile in a rectangular flow channel. Now, we are going to solve the concentration profile within the thin boundary layer. So, you can see that we need not to beyond the concentration boundary layer, the concentration remains same. So, we need not to have the full profile, we need to have the profile within the mass transfer boundary layer. If you see the profile of the velocity within the mass transfer boundary layer, it becomes a linear one. So, therefore, we linearize the velocity field assuming y square, h square and higher order terms will be negligibly small, they will be much less than 1. So, with this you will be having 3 by 2 u naught 1 minus y square by h square minus plus 2 y by h minus 1. So, 1 will be cancelling out, y square by h square is small compared to y by h, then you will be having 3 u 0 y over h. So, that is the linear velocity profile within the mass transfer boundary layer, and so this is the profile of u. Let us the v component since the mass transfer boundary layer is very thin. So, probably this will be in the order of 10 to the power minus 6 meter and half channel height will be in the order of 1 millimeter. This will be in the order of 10 to the power minus 3 meter. So, there is a order of there is 3 order of magnitude difference between delta and h. So, within this thin boundary layer, we assume that whatever the y component velocity is present in the wall, that will be remaining same within the mass transfer boundary layer as well. So, we assume that velocity is nothing but minus V w at the wall. So, with the help of 2 simplified velocity profiles, we can solve the concentration profile in the or advective equation within the mass transfer boundary layer. So, if you insert these 2 velocity profile in the governing equation, let us see what is the form of the governing equation. This becomes 3 u naught y over h del c del x is minus V w del c del y is equal to d del square c del y square. Now, let us make this equation non-dimensional. We make this non-dimensionalization as follows: c is equal to c by c naught, y star we write it as y by half height of the channel, okay, and the x star is nothing but x by L. L is the length of the channel, h is the half height of the channel in the y direction, and L is the length of the channel in the x direction. So, if you put this, if you put everything in the non-dimensional form, so y by h will be y star, this will be del c star del x star minus V w over h del c star del y star is equal to d h square del square c star del y star square. Then we multiply both side by h square by d and see what we get. 3 u 0 h square by d times L y star del c star del x star minus V w h over d del c star del y star is equal to del square c star del y star square. The right hand side is completely non-dimensional. There are 2 terms on the left hand side. If you look into the first term, this term is a product of 3 quantities. The second one is non-dimensional, the third one is non-dimensional, that means the other one has to be a non-dimensional term. Similarly, the second term on the left hand side, the second term is entirely non-dimensional, that means this has to be a non-dimensional quantity as well. So, if you look into the 3 u 0 h square by dl, this becomes you just express h, the half height, the half height will be in terms of equivalent diameter. So, this will be d by 4. So, this will be 3 by 16 u 0 d square by dl. Now, this term, if you open it, if you break it down into Reynolds and Schmidt, this becomes 3 by 16 Reynolds Schmidt d by L. And if you look into the V w by h, the V w h by d is nothing but 1 by 4 V w d e by d, and this will be nothing but non-dimensional wall velocity. We call it non-dimensional Pickley number. So, we call it P w Pickley at the wall. So, this will be a constant, and the V w h by d, this will be a function of x, because as you go down the length of the channel, the permission velocity decreases. So, this will be typically a function of x. Now, let us put this equation in the governing equation. So, this becomes a y star del c star del x star minus P e w del c star del y star is equal to del square c star del y star square. So, where a, the constant term, becomes 3 by 16 Reynolds Schmidt d by L. So, therefore, this becomes a constant, and we will be having the governing equation like this. Okay. Now, let us write down the boundary condition. At x is equal to 0, c was equal to c naught, the feed concentration. At y equal to infinity, c is equal to c naught. So this is the boundary layer, and this boundary layer is in the thickness of the boundary layer will be in the order of 10 to the power minus 6 meter, and the half height will be 10 to the power minus 3 meter. So it is obvious that anything here will be having a 0 will be having the same concentration as C naught. So we assume that the any place within the half height will be 10 to the power 3 times compared to the thickness of mass transfer boundary layer. So we call that as infinity. So at y equal to infinity, C is equal to C naught. At y is equal to 0, you have the mixed boundary condition, that is the solute, the convective term of the solute, whatever the solute is being convected towards the membrane surface will be is equal to the diffusion from the surface towards the bulk. So d del c del y will be is equal to 0. That means at the membrane surface the solute concentration will be more, and because of that there is it will set up a backward diffusive flux from higher concentration to the lower concentration, because the concentration of the solute at the wall will be more compared to the bulk. So it sets up a backward diffusion because of the Fick's first law. Now let us put these equations non-dimensional. So at x star is equal to 0, your C star is equal to 1, at y star is equal to infinity, your C star is equal to 1, at y star is equal to 0. We make it non-dimensional. So this becomes PEW C star plus del C star del y star is equal to 0. So these three are non-dimensional boundary condition of this particular problem. Now if you look into the governing equation is a parabolic partial differential equation. If you look into one of the boundary conditions, one of the boundary condition is residing at infinity. So this problem is a suitable candidate to admit a similarity solution. For progressing further with the similarity solution, we have to identify what is the similarity parameter. So for that, what we do, we evaluate the governing equation, we do an order of magnitude analysis of the governing equation at the edge of the boundary layer. So a y star del C star del x star minus P E W del C star del y star is equal to del square C star del y star square. Do an order of magnitude analysis. At the edge of boundary layer, and we have seen in the last class that the edge of the boundary layer, these two conditions are always satisfied. C star is equal to 0 and del C star del y star is equal to 0 at the edge of boundary layer. So this term will be off, and y star will be delta star minus 0. So this becomes delta star minus 0. Del C star is delta C star, and del x star is nothing but x star minus 0. This will be roughly del square C star. We have already seen this is nothing but some kind of delta C star or same order of magnitude, and delta y star square is nothing but delta star square minus 0. So this becomes a delta star cube, a delta star cube, del C star will be cancelling out. So this will be x star. So therefore we write delta star cube, delta star is nothing but 1 over x star to the power 1 upon 3. So delta star will be nothing but x star raised to the power 1 upon 3. So that will be the order of magnitude, that is the form of delta star, how delta star varies as x star. So it is varying as x star to the power 1 upon 3. So we can now in a position to define the similarity parameter. the similarity parameter now becomes eta, eta becomes y star by del star. So, this becomes y star by x star to the power 1 upon 3. So, that becomes the similarity parameter in this particular problem. If you look into the earlier problem similarity parameter was y star by tau to the power half, but in this problem it becomes y star divided by x star to the power 1 upon 3. So, we identified what is the similarity parameter. So, what is next is that to express all the partial differential of the governing equation in terms of similarity parameter. So, it becomes an the partial derivatives becomes the total derivative. So, we define del c star del x star. Del c star del x star is nothing but d c star d eta, and by using the chain rule del eta del x star. So, this becomes minus eta by 3 x star d c star d eta, and del c star del y star is equal to d c star d eta del eta del y star. So, this becomes 1 over x star to the power 1 upon 3, that is del eta del y star. This is d c star d eta, and del square c star del y star square becomes del y star of d c star del c star del y star, and this becomes del eta 1 over x star to the power 1 upon 3 d c star d eta del eta del y star. So, this becomes 1 over x star to the power 2 by 3 d square c star d eta square. So, we get the 3 partial derivatives in term of total derivative of dc of eta. So, we substitute this derivative in the governing equation and see what we get. If we substitute these 3 derivatives in the governing equation, we will be getting a y star minus eta by 3 x star d c star d eta minus p e w 1 over x star to the power 1 upon 3 d c star d eta is equal to 1 over x star to the power 2 by 3 d square c star d eta square. So, you multiply both sides by x star to the power 2 by 3. So, this becomes minus a by 3 eta y star divided by x star to the power 1 upon 3. If you remember, this term itself becomes the term in the bracket becomes eta. So, dc star d eta minus p e w x star to the power 1 upon 3 dc star d eta is equal to d square c star d eta square. Now, we have seen that V w the permeate flux, let us say non-dimensional permeate flux, is inversely proportional to thickness of boundary layer. More be the thickness of boundary layer, less flux you are going to get, but delta star is proportional to 1 over x star to the power 1 upon 3. So, this will be proportional to 1 over x star to the power 1 upon 3. So, therefore, P E w x star to the power 1 upon 3 is a constant, and that constant is, let us say this is a constant called B. So, the whole thing becomes a constant B, and let us see what we get. So, minus a by 3 eta square dc star d eta minus b dc star d eta is equal to d square c star d eta square. So, therefore, we change sign. So, d square c star d eta square is nothing but minus a over 3 eta square plus b d c star d eta. So, the partial differential has become an ordinary differential equation. So, the ordinary differential equation is easy to solve. So, you define d c star d eta is equal to z. So, therefore, we have d z d eta is equal to minus a by 3 eta square plus b z. So, we change sign. So, dz by z is nothing but minus a over 3 eta square plus b d eta. Now, we integrate it out. So, this becomes ln z is equal to ln k 1 plus minus a by 3 eta cube by 3 plus b eta. So, therefore, this becomes z is equal to k 1 exponential minus a eta cube by 9 minus b eta. Now, what is z? Z is nothing but d c star d eta. So, one more integration will give you c star as a function of eta. This one will be 0 to eta exponential minus a eta cube by 9 minus b eta d eta plus another constant of integration, that is k 2. So, this gives the complete solution of concentration profile. Now, these k 1 and k 2 has to be evaluated from the boundary condition. Let us look down the boundary condition at x star is equal to 0, at y is equal to 0, we had V w c plus d del c del y is equal to 0. In the non-dimensional form, this becomes d c star d eta plus b c star is equal to 0. To bring this, so this is at eta equal to 0. So, to get here to here, which has expressed del c del y in terms of d c star d eta, and I omitted one step, couple of steps here to get this equation. And at y is equal to infinity, we had c is equal to c naught. So, at y star at eta is equal to infinity, we had c star is equal to 1. So, this is boundary condition 1, and this is the second boundary condition at eta is equal to 0. Now, with the help of these two, one can evaluate the constants k 1 and k 2. So, if you do that, so this becomes c star eta, this becomes k 1 0 to c star eta is equal to 1. So, this becomes k 1 0 to infinity exponential minus a eta cube by 9 minus b eta d eta plus k 2. So, this is a definite integral because a is constant, b is constant. So, we call this constant as I. So, 1 is equal to k 1 I plus k 2. Now, if you put the other boundary condition that d c star d at eta is equal to 0, d c star d eta plus b c star is equal to 0. So, what is d c star d eta? D c star d eta is nothing but k 1 exponential minus a eta cube by 9 minus b eta. So, this will be k 1 exponential minus a eta cube by 9 minus b eta evaluated at eta is equal to 0 plus b c star evaluated at eta equal to 0. That means, this will be 0 to 0. So, the first term will be gone. So, this will be b k 2 is equal to 0, and at eta is equal to 0, exponential 0 will be 1. So, k 1 plus b k 2 is equal to 0. So, we will be having k 1 is equal to minus b k 2, and now we have two equation and two unknown in k 1 and k 2. You can solve them. So, if you can solve them, this becomes 1 is equal to k 1 I plus k 2, and put k 1 is equal to minus b k 2. So, this becomes minus b k 2 I plus k 2. So, we can get k 2 as a as an explicit expression 1 minus b I, and k 1 is equal to minus b k 2. So, it will be minus b 1 minus b I. So, we get the total concentration profile as a function of eta. So, this becomes minus b 1 minus b I 0 to eta exponential minus a eta cube by 9 minus b eta d eta plus k 2 is nothing but 1 minus b I, where I is the definite integral 0 to infinity exponential minus a eta cube 9 minus b eta d eta. So, once we know the value of b, we know the value of a, we can completely plot C star as a function of eta. One can also plot C star as a function of y and x by a combined variable, because we know the form of eta is nothing but y star by x star to the power 1 upon 3. For a particular y value, we know the value of eta as a function of x star, and we evaluate this profile in the in a loop of x star. So, we can plot C star as a function of x star. Similarly, if you would like to plot the C star as a function of y star at a fixed value of x star, one can do that as well, the same way we have done it for the profile of y star. So, therefore, by using similarity solution method, one can solve the partial differential equation by boiling it to ordinary differential equation, and the solution of ordinary differential equation is pretty simple. So, I stop it in this I stop the whole this class at this point. In the next class, I will take up one more solution technique of partial differential equation, that is the integral method of solution. Thank you very much.